Hello, my name is Xie Lianxin. I'm going to introduce our work BP3, Parameter-Aware and Progressive Phase Retouching with Limited Paired Data. The proposed model can be used to perform progressive phase parameter removal. We leverage the merits of both encoder, decoder, and generator architectures, seamlessly integrating them into a unified framework to effectively address a wide range of facial parameters. A parameter-aware attention module is incorporated to enhance the collaboration between the components by refining the intermediate features that are transferred among the components. To reduce the dependence on paired training data, we leverage unpaired training data to regularize the proposed framework. Let's take a look into the details of different components. First of all, we introduce the parameter-aware attention module. This module takes incoming features and produces a soft mask or attention map, which is expected to highlight parameters. According to our observation, identifying parameters heavily depends on the surrounding scheme. In view of this, we adopt the several convolutional blocks to learn the parameters alpha and beta of sigmoid function at local regions. To recalibrate the encoder features, we can suppress the parameters by reducing the response in the attention map, and adopt the convolutional block to infer the weighting maps. This module is jointly optimized with other components in the training process. After introducing the attention module, we began to enter our overall framework. At the first stage, the decoder performs cross-retouching on a raw image, conditioned on the weighted encoder features. For the paired training data, the retouching ground truth is available, so decoder is encouraged to infer the ground truth as accurately as possible. In addition, for any retouched images, decoder is required to recover them. When the parameters are large, the first stage may perform less satisfactorily in surfacing clear face images. We exploit the merits of StyleGAN 2 and design the second stage, where the generator receives the latent code inferred by the encoder as well as the weighted intermediate features from the decoder. Similar to StyleGAN 2, the features from encoder is fed into a MLP to obtain a style code that is broadcasted to each block for feature normalization. On the other hand, the features from decoder provides rich image information, which largely alleviating the difficulty of synthesizing high-fidelity image. An attention module, which prevents the generation process from producing parameters. Finally, we impose the pixel level and perceptual consistency regularization on generator and decoder. In the BP3 model, we use parameter facial images to guide the model to pay more attention to the parameter regions on the face. When provided with any parameter image, the frozen BP3 generates a parameter mask. We consider the mask as a weight map to guide the discriminator to pay more attention to the discrimination of parameter textures, rather than limited to the quality of generated images. Like the above methods, attention mask was also used to guide BP3 to pay more attention to suppress the generation of parameter textures and deceive the discriminator. Here are the loss functions used to train different modules of BP3. All of them are jointly optimized. We visualize the attention maps ME to D and FD to G, and the corresponding synthesized image, tilde S and hat S at two stages. The delta in the fourth corner denotes the difference between the raw image and the retouched. We observe that both attention maps cover most of the parameter regions, indicate in the different map delta. Compared to the first stage, The second stage focused more on synthesizing the details, and the high response area in app D to G is greater than that in ME to D. As a result, the second stage is able to produce clear face images with realistic details. We evaluate TBP3 on selective FFHQR images with large pose, occlusion, and dim illumination. As the figure we can see, BP3 is able to achieve stable performance in their case. We also use white images to evaluate the generalization performance of BP3. We can see that BP3 can handle serious facial blemishes. Here is the result of extent experiment on inpainting. So in this work, we propose an attention-guided progressive face retouching framework to remove blemishes laterally and synthesize high-fidelity content. We designed a two-stage structure to explore the merit of the ULED architecture in restoring the image details and that of the GAN generator architecture in generating realistic images. The core idea is to explicitly suppress blemishes when transferring the intermediate features from the encoder to decoder, and from the decoder to the generator. To the end, we adopt a blemish-aware attention module to learn the weighting maps. That's all. Thank you.